So this is problem number 1 that's on your sheet over there. So this formula represents a calculation involving the rate of decay expressed in disintegrations per unit time. So A is the rate of decay, N is the initial number of atoms, and T is the half-life. So what we're interested in knowing is, let's see. Okay, let me see what we got here. Okay, what's our final answer got to be? Well, we're interested in knowing if we have a material, given that we know its half-life, and we know the initial number of atoms, what is the rate of decay of that material? In other words, we got a gram of this stuff, and we know its half-life is 30 days, and we want to know initially, when we're just starting at that point where it's just that stuff before it starts decaying, how many disintegrations per second we're going to get out of this material. Okay, so we know the material, we know its half-life. We don't know how many curies or becquerels that this is emitting. That's how many processes per second that this is going through. So that's what we want to find out, the initial, and then as it happens, it's going to be less and less of the material left. So we want to decide, that's what we want to use this equation to determine. Okay, and again, that's disintegrations per second. Curies is just another version of that. Okay, so what is the initial decay rate per minute of, so first of all, number 1, we see right away something that's throwing a little curve here because we know becquerels is per second, curies is per second, of 1/10 of a milligram of sulfur 35. They were nice, gave us the half-life. We didn't have to go back to that other slide. How many curies does this sample represent? So what was our equation again? Our equation was that's the wrong equation. Okay, A is equal to 0.693 times N. N is the number of atoms. So if we have a 1/10, where'd it go? Yeah, going in the wrong direction. If we have a 1/10 of a milligram of sulfur 35, how many atoms do we have? Anybody propose a way to figure out how many atoms there are in a 1/10 of a milligram of sulfur 35? Moles, exactly. Avogadro's number. We know Avogadro's number, right? So we're going to take Avogadro's number, which is 6 times 10 to the 23rd. We're going to take, how many moles is a 1/10 of a milligram of sulfur 35? Did they give us the molecular weight of sulfur 35? Well, let's see. We know it's 35, right? I mean, that's the molecular weight. That's the total number of neutrons and protons, I think, right? Am I right about that? Yes, I am right about that. So the molecular weight is 35, right? How many grams of this stuff do we have? We got 0.1 milligrams. We got 0.001 grams, right? So 1 gram, 1 molecular weight in grams represents 6 times 10 to the 23rd atoms. So how many do we have? Well, the fraction that we have of it is 0.001. Remember, it's milligrams, not grams. 0.001 over 35 is the number of moles that we have. Everybody agree with that? In other words, I'm converting this into grams. So in grams, it is 0.3 zeros and then a 1. I got to move decimal over 3 places. Divided by 35. That's the number of moles we have. Anybody got a calculator? Do that calculation. I'm going to hook up my graphics tablet, so maybe I can work with you in the next one.
2.8 to the power of 10 negative 56.
2.8 times what?
10 negative 6.
Okay, let me see if I can write that down. Okay. So I can't get this to connect. (2.8) times 10 to the minus 6. Everybody agree with that? Somebody else did it? I'll take your word for it since you're the only guy that did it. That's okay. That's close. That's close enough. Don't worry about it. That's close enough. Okay, so that's how many atoms that we have, right? Okay, so let's go back to the equation. The negative 10, negative 5. Okay, so it's 2.8. Which one did we decide it was? Negative 6. I got to flip back and forth to pen the pointer here. 2.8 times 10 to the negative 6 molecules, right? That's a number. That's the number of moles. Now, how do we know how many atoms that is? We got to multiply it by 6 point. What is it? Do you remember? 6.02 or 2? 6.02 times 10 to the 23rd. Okay, what do we wind up with? We wind up with roughly, that's 3 times 6 is 18. I'm going to call it 17 times 10 to the minus 6, 10 to the 23rd. Conveniently, that's 10 to the 17th, right? We all agree with that? I hope we all agree with that, right? So that's the number of molecules that we have. That's our N. Okay? And what's our half-life? Our half-life was, anybody remember? What was it? How many days? How many minutes? Was that what it was? 87.5 days? Well, wait a second. We need to know this, I guess, in minutes, right, is what we were looking for. Number of disintegrations per minute, right? So, initial rate of decay. So, how many? 87.5 times how many minutes in a day? There you go. There's somebody that works with something where you got to figure out how many minutes are in a day. You have to organize. I can tell you how many days there are in a month, how many days there are a day, because work with cooling, when you work with heating equipment, process equipment, and stuff like that, chemical engineering, you need to know this stuff. Right? Okay, so that's 87.5 times 1440 is the number of minutes that we're dealing with. Right? That's our half-life, so that's going to wind up down here. Now we're working in minutes at this point. Right? So we're going to take 0.693 divided by the number of minutes that this comes out to. I'm not going to do it right here. You can give it a try at home. Times the number of molecules that we're dealing with. 17 times 10 to the 17th, or 1.7 times 10 to the 18th. Okay. 1.7 times 10 to the 18th. A lot of molecules in 10th of a milligram. So, and this is, let me estimate this. This is say times 10 times 100 times 100. 14, say 12. That's roughly, I'm going to say that this is roughly 120,000 minutes. 126? Okay, so that's 1.26 times 10 to the 5th, right? And so we're going to multiply 0.693 times 1.7. What does that come out to? About 1? A little bit more than 1? I'm going to call it 1 since nobody's saying anything. I'll say 1.2. And then that's our 0.693 divided times that. Then I'm going to divide that by 1.26. So that's going to be roughly 1 times 10 to the, this is 18 divided by 5, 10 to the 13. Okay, that's a wild guess. All we're going to do here is we're going through the process of actually calculating it. Maybe the next one we'll actually do the physical numbers. We'll do it right. I'll pull the calc. One of the reasons they didn't do it because I got to exit PowerPoint in order to get to my calculator here. Okay, so this one I think is simple enough that you can just substitute the numbers. You just got to be careful of your units. make sure that you don't get confused by milligrams and grams for calculating how many moles, that you don't get confused by seconds, asking you for the decay rate in seconds or minutes and so on and so forth, or supplying you the half-life in minutes and so on. Just make sure you don't get crossed up by the what I'll do is that there'll be a similar problem to this on the homework assignment, and that one I'll make a video and I'll work through it very carefully. So I just want to get this first one out of the way quickly.
What's the unit for initial?
You want to know something? That's a great question. And the reason why it's a great question is because, did you take industrial ventilation? There's a lot of formulas in industrial ventilation that you have two formulas side by side. You have one for standard units, one for metric units, right? And then there'll be numbers like this just floating in that formula. And that number will be Newton meters per square. It'll have many different units in it. And those units will be units that in that constant that you're using, that will clean out all those units and give you the result in cubic feet per minute. That's what this 6.693 does. To tell you what it is exactly, I'd have to actually do a dimensional analysis here. The N is, what's N? N is disintegrations per second or minute, right? Oh no, the N is the number of molecules. It's a number, right? It's just a number of atoms, right? T is half-life is minutes or seconds is days. We've converted into minutes, so T is now minutes, right? So, and we got the N from. We started with, what did we start with? We started with milligrams. We converted that into atoms, right? We multiplied by 6 times 10 to the 23rd, converted it into moles, right? Then we multiplied the moles by atoms per mole, 6 times 10 to the 23. The moles drops out, so it's just atoms. So we have, so N is atoms, right? T is minutes. So this winds up so it's dimensionless. It has no dimensions. Okay.
I guess what I'm showing.
Yeah. What is that? What is that?
No, but in exercise where you're being asked disintegrations per minute.
Right.
And then by definition, a Becquerel or a Curie is a per second. Right.
Except you're not really being asked that. You're being asked, the decay rate is expressed. Is that what you're being asked there?
How many Curies?
I can't get to the question right now. You're right. You're right. We just figured out what the disintegrations per minute were. Right. So now you got to multiply it by 60 to get the number of becquerels that you have. And then you have to divide that by 37 billion to get the number of Curies that you have. Right? Are we all on the same page there? I'm right about that, right? I hope. Okay.
So A initial is basically the
disintegrations per whatever unit you use. Yeah, whatever unit you use there.
Okay. So we figured out the second for the.
Yeah, you wouldn't have to bother with the conversion after this if you had converted it into seconds instead of into, right?
So this equation, does it always give you becquerels?
Yes. Disintegrate. It'll always give you. This is the number of disintegrations per unit time, and depending on how you express half-life, whether it's days, minutes, or seconds, right? That'll determine how many disintegrations per what amount of time. So if you convert this into seconds, you will have becquerels.
It gives you becquerels instead of Curies
or. Well, no, hang on a second. Yes, it gives you disintegration per second, right? Which is a definition of a becquerel, right? But then if you wanted in Curies, you would have to do that conversion from 37, the number of becquerels per minute or per second, right? Rather per second, right? Then you would have to divide that by 32, whatever it is, 32 billion, 3.2 times 10 to the 10th. What's that? I'm sorry, what's that? That's Avogadro. You use that. Avogadro's number is also just atoms.
No, the other radiation units, cigarettes or something.
Oh, hang on. That's way down the line. See, that's the thing that's confusing about this. This is the simplest form of describing how much radiation is present. How many times is something disintegrating? How many times is it releasing an alpha particle? How many times is it releasing a beta particles? Now that we know that, how much energy is that? In other words, if you hit something with that, how much energy you're translating, right? So when you talk about energy now, you're talking about energy per. In other words, if it's an object or a person or a dog, now you're talking. Well, if I have this and it's hitting this dog, how much energy is being transferred to the dog? Then that's energy per mass, right? So now joules per a kilogram now is like the next thing we look at, and then if it's beta particles, it's going to be different than even though it's the same number of particles, the effect of beta particles is going to be different than the effect of alpha particles, is going to be different than the effect of gamma particles. So now we got to take that energy that's being transformed and adjust it for what the biological effect is. So that's how we get to rads or sieverts, and that's how we get to REM. Actually, sieverts and REM, which is rads are the Röntgen dose, something like that, and REM are Röntgen equivalent dose. In other words, it includes a correction factor for the biological effect of the radiation. So you got the actual amount of particles being released and disintegrations that take place. Then you got a measure of how much energy is being delivered by different kinds of particles are given at that rate. And then finally, you got a qualifying factor, an adjustment for what the biological effect for that kind of radiation is. And it's different for each different kind of radiation, different energy.
Never actually talked about it.
This is not even, Yes, because it depends on what part of your body is exposed, how it's absorbed, and so on and so forth. Some organs are affected more than others, even though you only use a single qualifying number, usually for, like a human exposure or something like that. So, all of this stuff is kind of a kludge that you're forced into because you're trying to define a quantity, which is really any permutation of a dozen different things. This particle, this rate, this energy, hitting this kind of thing, being absorbed, having this health effect, and so on and so forth. So you got this whole cascade, this whole, permutation of different effects, different quantities converted into energy, converted into health effects, and so on and so forth. So it's really kind of like it can get very confusing. And also, so we're going to try and step through this in a manner that kind of keeps it a little bit organized, right? So far, all we have dealt with is the number of disintegrations per second. That's our only measurement of radiation so far. It might be electrons being produced, beta particles, it might be alpha particles, it might be X-rays, it might be gamma rays, but all we know so far is we're counting how many X-rays, how many beta particles, how many electrons are being created every second. And let me escape this and clear this junk off of here. And now, at this stage now, I'm really sorry I didn't just go through the calculation and get everything set up here so I could and drop out of this. We could have done it carefully. We'll do the next one that way, though. Okay, half-life calculations. So now, calculate how much radiation will remain after a given time. We use the following equation. We're going to use the left-hand version of this, which I think is just, I think the real key here is that this is an estimate of this one where you don't have to do work with natural logs. So what are we looking for here? Why might we be interested in this? We might be interested in this because we are concerned that we've contaminated a space. Hopefully it's a material that has a short half-life, and we want to know how quickly this stuff is going to go away. So A is the radioactivity remaining after the amount of time has passed, the small t has passed. T1/2, of course, is the half-life of the material, and A1 is the initial amount of the material that's in the environment. So now we're going to go to the next page here. After a radioactive release of iodine-131, we know it's got a short half-life, so we might be interested in this in real life, right? Radioactive release of iodine-131, half-life equals 8.04 days of the power plant. There was 500 picocuries of activity in the air. Okay, what is the activity in 30 days? How much is it? How much has the radioactive iodine diminished in 30 days? Well, right off the bat, I'm looking at this. I'm saying 30 days. Picocuries of activity. What is that? That means the number of disintegrations that you're getting per second is actually that picocuries is really thousands of becquerels. So there's 500,000 disintegrations per second. Amazing, right? That you get that kind of stuff. 500,000, because remember, so we have 500 picocuries. I'm wrong about that. We have to do a ratio, because a curie is 32 million, and so 500 picocuries is how many becquerels? Anybody want to calculate that? Let's not bother. Let's not bother. Okay, just stay with. Just know that is an equivalent number of decay, of radioactive decays per second, right? Whatever that turns out to be. What is the activity in 30 days? Well, right off the bat, I can see that half-life is 8 days. After 8 days, it's half of that. It's 250. After another 8 days, right, 16 days, it's half of that, 125, right? After another 8 days, which is now up to 24 days, it's half of that, it's 125. But now I'm not going to go another half day. So 25, so maybe one more week, it's half of that. So it's somewhere around 60 picocuries per liter is what we expect the answer to be. Let's actually do the calculation now. Okay. So we can't get the formula over here and this at the same time. Good. Okay, so let's do this. So I'm going to... every time I touch something here, I got this graphics tablet, I got my trackpad, I got this. Okay, every time I touch something messes up. Let me get this down here. Okay, so we got a formula here. So let me make sure I got a pen. Okay, so A equals A initial, amount of radioactivity, times 0.5 to the T. What is T? T is 30 days, right? We may have to do some conversions, over the half-life, which is 8.02 days. Look at that. Okay, days canceled out, so that's just a number. So let's see what that is. My calculator. So that is 30. Let me clear out my memory here in case I've used this before. Oh, my goodness. I'm going to switch out of the pen. Okay, clear. Which is so 30 divided by 8.02. Oops. Yeah, let me get it on here so I can stick it into memory here. 30 divided by 8.02 is equal to, as you said, 3. I got 3.74. Oh man. Okay, you guys want to just now, you don't have to look that hard. 30 divide, you know what it is? The computer is the worst possible thing to be trying to use as a calculator. 8.04 was it? Okay, 8.04. Okay, good. So now I got the answer you got, I hope. So I'm going to put that into memory plus. I'm going to clear that out. So now I'm going to take 0.05 rather, and I'm going to take it to that power. So x to the y, so I'm going to click on this, and then I'm going to recall memory, which is going to be my exponent, and I'm going to ask it to give me the result. So that is 0.075, etc. Okay, so this whole value is 0.075. So now I'm going to multiply it by the initial radioactivity, which is 500 picocuries per liter, times 500. And I get 37 picocuries per liter is what the activity is at that point. when we did a rough estimate, I got kind of an order of magnitude. I think it was around, I said 60 or something like that. But I wasn't really compounding it, the way a half-life really would work. Right? Okay. Yes. Tell me I did it right. Yes. Okay, good.
You said 37.5 picojoules per meter.
Yes. Well, the only units that are left, these units cancel out. The only units that are left are what we put in here.
Yeah.
No, yeah, you're right. I just assumed per liter. Right. Exactly. You're exactly right. It doesn't say that there. Okay. Okay. Everyone on the same page with that. Okay. The reason why I gave these out is so that you guys could do this yourselves as well. Okay. Let's do it. Let's try another one. Let me clear this out. Okay. So, and also these examples, this course, there's a lot of interesting stuff in this course, but there's a lot of formulas and a lot of calculations and stuff like that. As much as possible, I'm trying to make the assignments and take advantage of what we have in the PowerPoints, at least the calculations that might, in the real world, might be something that you might be interested in. Like if you have a release of iodine, you want to know how fast it's going to decay over a period of time. Okay, so let's see what we got next here. Okay, what activity would remain of 1 curie of cobalt-60? Here we go, that's yours. 5.24 years half-life after a 20-year period. So those machines must be very sensitive to the amount of energy that they, because a couple of years is not very long in the half-life of cobalt. What's that? Oh, cobalt-57. There you go. Okay. Yeah, I guess cobalt-60, you probably need they have to follow you around with an armed guard or something like that, probably. Yeah, that makes sense. Okay, so yeah, this stuff lasts a long time. 5.24 half-life after a 20-year period. So maybe this is like some cobalt that you use in a medical device or something like that. So you want to know after 20 years how much of this material remains. Okay, so we're going to use the same formula, right? Okay, so what would we be doing there now? Yeah, let me get my pen here and use it. Okay, pen. Okay, so A is going to be equal to A1, which is 1 curie, times 0.5 times, let's see, we got 5.24 years over, now we got to convert 20 years, 20 times 365. Okay. I'm sorry.
Well, first, I think it's 20 on the top of that.
Oh, you got years. I'm sorry. Yeah, you're right. It's time over half-life. Oh, you're right, 20, and the half-life is down on the bottom. But I can't see shit up here. That's my problem. I'm recording this now. That's in posterity. Okay, so because I'm working with you've seen this giant thing up here. But you got to remember, I'm working with these tiny screens here. Okay, so where was I? 20 over 20 years. The half-life is the period over the half-life, which was 5.24. Okay, so let's do this calculation. I'm trying to juggle the pen and turn the pen on and off and get the pointer back. And 30, let me make sure I cleared out the memory. Huh? Yeah, but that's straight. If it was a regular keyboard, I would do that. But they're straight lines, even more annoying. 30 divided by, I'm sorry, not 30. 20 divided by 5.24 equals this. Oh, crap. I bounced and hit that. Well, I need to put it into memory so I can do the multiplication. Divided by 5.24, was it? Am I blocking it? 5.24 is equal to 3.81. Let me put that into memory before it gets away. Times, oh, I'm sorry. Actually, I don't want to times. I want to, let me clear this out. I want to take 0.5. I want to take it to that power. Recall memory equals, so it's 0.07 again, times, which is kind of the ratio of the half-life to the period of time we're talking about. Is almost the same thing as before, so that makes sense. Times 1 curie. Well, it's 0.07 curies is basically what we wind up with. Okay, everybody okay on that? Good. Okay, good. Let me clear up memory. Let's see if we got another one we can get to. Let's actually look at this one. Look at this. Oh, no. What have I done? See, this works better at home when I was doing it like, on a table. But it is better if we do this together, I think, in the long term. Where was I here? How are we doing? Oh, you didn't get both pages?
Looks like I took a few of the same. Was this your copy?
Where are we? That was example number 3. That's the one I want to start with. Okay. Biological half-life. Okay, so we know that this material, this radioactive material, is going to decay. Nothing in the world is going to stop it from decaying. It's headed to lead no matter what you do, anything else that happens on Earth. We get struck with a meteor, we're wiped out, there's an apocalypse, there's zombies, doesn't matter, it's going to decay. Right? It's a physical process, it's going to happen on its own. We can run a clock off of this. This is so predictable that this is going to occur. Right? And in fact, they have. I think whatever they use now is the standard for time now. I think uses some sort of it measures radioactive decay or something like that. So at any rate, this is the rate at which this stuff is going to decay. Half-life is very predictable. So now let's say this stuff gets into your body. You have 2 issues now. It's in your body, right? And it's starting to decay. So over time, the amount in your body is going to go down because it's going to decay. So it's got a short half-life. It's not going to stay in your body forever. It's eventually going to decay into either something also radioactive or something not radioactive, right? So it's going to decay in your body. But on the other hand, at the same time, your body is going to be excreting it, right? Your body's going to be metabolizing it. If it's iodine, it's going to collect in your thyroid. But over time, you're going to use that, and it's going to go out of your body. So you have 2 half-lives now. You have the half-life, the physical half-life, and you have the biological half-life. In other words, the rate at which your body expels it and the rate at which the stuff that stays in your body diminishes just because it's breaking down. So we want to combine the 2 of them. In other words, if you ingest a certain amount of this stuff, or you breathe it in, or somehow are you supposed to, if you get a certain amount of stuff into your body, how fast are you getting rid of it, right? And that's a combination of those 2 things: biological half-life and the physical half-life. Okay, that's called the effective half-life. And we have a formula over here. So the effective half-life is equal to the radioactive half-life times the biological half-life over the radioactive half-life plus the biological half-life. It's kind of like a weighted average of the 2, right? So if we have an example of this, the radioactive half-life of iodine-131 is 8 days. Thank you for not adding digits to that. This radionuclide concentrates in the human thyroid gland where it has a biological half-life of 30 days. It's going to hang around the thyroid with a half-life of 30 days. What is its effective half-life in the thyroid gland in days? Okay, so let's calculate that. And that's going to be our last one because the class is over at this stage. Okay. I know you don't want to do that. You don't want to go. You want to keep doing these things for the rest of the night. But unfortunately, this is fun, right? This is not, I think now that we relax and we can do these a little bit more casually, I think this is more fun than the noise was. The noise got a little complicated. A lot of the examples we had on the noise were like really arcane. You had to do 14 calculations to get to the answer. Right? So, okay, so at any rate, a little challenging, but whatever. So our effective half-life is equal to our, let me see if I can read that, our radioactive half-life. What was our radioactive half-life? 8 days. Times our biological half-life, which was how much? 30 days? Okay, so it's 8 times 30 is days squared over 8 plus 30 days. Units up here are days squared. Units down here are days. So it winds up the units being in days, or half-life in days. So it's going to be 8 times 30 is 240 over 8 plus is 38. So 240 over 38 is our effective half-life is 240 divided by 38. And then we'll say goodbye. I need to find a toggle to turn on or off easily the pen and the pointer. Let me clear this out. Okay, so 240 divided by 38 is equal effective half-life of 6.3 days. Radioactive iodine is going to hang around. It's going to have half-life of 6.3 days in your thyroid. And so if you have a milligram of it, you have a microgram of it in your thyroid, right? In 6.31 days, you'll have half a microgram, and so on and so on and so on. Okay? And part of that will be lost because it's decaying, and part of that will be lost because your body is excreting it. Good night, guys. So this is an interesting session, right? We had some interesting stuff going on here. Oh, by the way, who was talking about impact sound on the impact meters for sound? I found an article. I'll post it on Blackboard. Whoever brought it up, I have an article. I'm going to post it. The meters that we have here do not measure impact. They only measure short-term and long-term, fast and slow, 35 milliseconds. But it is true that there are instruments that will measure very short-term impact exposures. So I'm going to post that article.